3.5, transformations of exponential functions. This is not in your workbook, so just look and listen and think. Basically, what we're going to walk through is you've done transformations of polynomial functions, you've done transformations of root functions. Now we're doing transformations of exponential functions. You're just, what's a transformation? Well, it can be a translation where you just move it up and around, left and right, up and down, or it can be a stretch compression. So we're going to talk about just basically right now is just translations, so moving things left and right or up and down. And a couple of things, right now I'm just going to draw on each graph. I'm going to draw the graph of y equals 3 to the power of x, okay, to give us a reference. Looks kind of like that. It goes through 0, 1, 0, 1, 0, 1, and it grows by a factor of 3 every time. Now, what do you think, what's your guess? What is this minus 4 going to do? Where's it going to move it? What's it going to do?
Down 4.
It's going to take the whole curve, the exact same curve, and move it down 4, okay? The best way to do this is to think about the asymptote, which the original asymptote is the line y equals 0, or the x-axis. Okay, there it is. There it is. But this asymptote is going to move down 4. 1, 2, 3, 4. Okay, which means this point, 0, 1, is going to move down 4 to be 0, 3. And now I'm going to try to draw the exact same curve coming through here. Okay, we've taken the same curve, we moved it down 4. Okay, good. So this, when you tack something onto the end in addition or subtraction, it's going to be a vertical translation. This, in this case, 4 units down. What about this one? Left, right, up, down?
I'm guessing to the right.
Good. Yeah, it's going to take this curve and move it 2 to the right. So every single point that we have, it's not going to change the shape, but it's going to take every value and move it 2 to the right. 2 to the right. 2 to the right. 2 to the right. Okay? So it's coming across more before curving up, and then it curves up 2 units to the right the whole way up. Good. What about this one?
It's going to go to the left 1 and up 3.
To the left 1, pulling it over here, 1 every single point, and then up 3. So instead of going through 0, 1, we're going to go 0, 2, 3, 4, and pulling it to the left. So it's going to start curling up a little bit earlier. And it's going to look something like this.
Shouldn't it be in brackets? The x plus 1.
That's a good question. Shouldn't this x plus 1 be in brackets? It doesn't need to. They're both clearly in the exponent. Okay, so it's a natural group. You don't need to write the brackets. You understand that's a group. You're dealing with that together. Okay, good. You could also have a multiplier out here, in which case you'd be stretch compressing, which we will talk about right now. Okay, vertical and horizontal stretches, compressions, and reflections. So what do you see here?
Oh, it's a vertical. Stretch
Horizontal compression.
Yeah, good. Horizontal compression. Okay, so we have 4 to the power of x, kind of. It's actually 4 to the power of 2x. So every time before we take this exponent, whatever goes in for x is going to get doubled, and then we're going to take 4 to the power of that. So is this going to grow faster or slower?
Faster.
It's going to get taller faster. And because it's attached to the x, okay, this is a horizontal compression by a factor of 1 over k. Right? It's horizontal compression by a factor of 1/2. So if this is our original 4 to the power of x, okay, then every single point along this curve is getting pulled in half the distance. It's going to take half as much x power to make it grow just as high. But watch this, it goes through the same y-intercept. It actually starts lower and comes up faster.
take care of it.
That is a nice full angle.
Okay. Okay, next one. We have a base power of 4 to the power of x. So I can put that in here. And what's happening to it?
It's a reflection.
There is a reflection in the x-axis. And what else?
And vertical stretch.
Vertical stretch by a factor of 2. Okay, vertical stretch by a factor of 2. So again, whatever is easiest for you, okay? You can apply the stretch first. Vertical stretch by a factor of 2. That means every point here is going to be twice the distance. Yeah? Still goes through the same point though, because we haven't moved it. And then you can perform the reflection over the x-axis, which then I would mirror from here down to here and from here down to here. Again, you would have, if you have a graph and a grid, then you have these points. Then it's really easy to just take this value and make it negative, put it down here.
So when do you change your point on your x-axis? Or your y-axis? Yeah, no, your y.
So we can, ooh, no, I'm wrong. You're right, I'm wrong. It does not go through this same point. It goes through this, the brown one is going through 0, 1. This one goes through 0, 2. Which means this goes through 0, negative 2. Okay? It has been stretched. If x is 0, then 4 to the power of x is 1. Times 2 is 2. So 0, 2. Sorry, you are right. It did change there. Yep. So this red curve has been reflected and stretched. And again, you can do those in either order. Okay, in our last one, we have a base of 4 and a power of negative 1/2 x. So what do you think we're going to do here? What do you see?
Horizontal stretch.
Yes, we have a horizontal stretch by a factor of 2. So it's going to be out here, but what does that negative do?
Reflection on the y-axis.
Reflection over the y-axis. Okay, so again, you can do it in any order you want. I'll do the stretch first. Every point now is going to be twice as far away, right? Still going through this same point though. Horizontal stretch. And then we have a reflection over the y-axis. So this, it's a terrible drawing, but these should be the same. I didn't want to bump into that guy, but I guess I should have. Yeah, make sense? These points should be 1, 2, 3, 1, 2, 3. Okay, good? That's the basics. So we did a set of 3 that were just translations. Now we did a set of 3 that were just stretch, compression, reflection, both horizontal and vertical. Okay, basics of transformations to exponential functions. So here are all our parameters, right? A, K, D, and C. Just like when we're talking about other types of functions, you can write things. This is the general form now for exponential functions. So what do they all do? What does A do?
Vertical stretch or compression. Reflection over the x-axis.
Okay, A is vertical, stretch, compression, or reflection. B is the base of your power. So it's not a parameter, it's going to be a value that's going to be given. Okay, now what does K do?
Horizontal stretch, compression, reflection over the y-axis.
Horizontal, stretch, compression, reflection. What about D?
Horizontal translation left or right, which is horizontal.
And C?
Vertical translation.
Good. Okay, now, what does this mean? We're not going to do this in this example, but in your practice problems, I'm certain you'll get something like this. You'll get g of x is some function of a times the function. And then here you might have something like, well, I'll write it all. K x minus d plus c. Okay, this is just telling you that g of x is the function f of x transformed according to these four parameters. Now you say, well, that doesn't look like an exponential function. But if they tell you that f of x is 2 to the power of x, now you know that g of x is this function with these transformations. What does that look like? Well, that tells me that g of x is I have a base of 2, and then to my x in the exponent, I'm going to have k times x minus d, all in the exponent, because that's where x is, and this is what's happening to x in my transformed function, and then at the end plus c. Okay, so they might give you something that looks like this, and it's really hard for our brains sometimes to think. We right away look at that and we say, oh, it's x to the power of 1, so it must be linear. No. Or, well, it kind of looks like vertex form, so it must be a quadratic. No. Okay, all this thing does is explain what transformations are going to happen to the given parent function. If the parent function is exponential, this is what it looks like. Okay? Just to say that one other way. What if my parent function was quadratic? Okay, well now my new function g of x, based on the exact same given transformations, is now y equals ax, nope, a times k x minus d, close that, squared plus c. Okay, now I have all the same parameters. My function notation is gone. My reference to the function f of x is gone, but it's squared. So now this actually is vertex form of a quadratic. Okay, so now we get into our actual example number 3. We're going to graph something in this form, and this is what we get. It's real complicated. We get y equals -2, and as I'm writing it, think about what it's going to do. Okay, -2 to the power of 2 times x minus 3 plus 5. Now you could try to go through a table of values for this. And that would work. You could do an extended table of values, right? And you'd eventually get to where you want to go. But sometimes easier way to do it is just to perform the transformations in order and just graph it out. So graph out one of the transformations, then add another transformation, then add another, and your graph will change over time to what it's supposed to look like. First thing we want to do is identify what these things are going to do. So let's be specific. We have an a value of -2. So what is that going to do?
Vertical stretch by a factor of 2.
Oh, careful. I misspoke. What is this actually?
The base.
It's the base. So what is a?
Reflection. 1.
It's just -1. So what does it do?
Reflection of the x-axis.
Reflection in x-axis. Good. Because I'm using blue, let's go over to C. What is this going to do?
Vertical translation by a factor.
5 units up.
5 units up.
Oh yeah.
My factor of 5 units up.
A vertical translation up 5. Okay. K.
Horizontal compression by a factor of 1 over
1 over something. 1 over 2, yeah.
And this guy?
Horizontal translation, 3 units left. Right. Oops.
I was the only one who said right.
I didn't hear you. I didn't say anything.
Horizontal translation 3 to the right. Okay. So now that we have that information, let's get into graphing it. You have 3 different graphs there that are going to help you to do it. So I'll try to do it the same way. And we're going to start with just our standard 2 to the power of x, right? 2 to the power of x, you can think about a couple of the points that it goes through. 2 to the power of x goes through 0, 1. And it goes through 1, 2. And it goes through 2, 4. And can we pick another one? It goes through 3, 8. You can pretty much figure out what's happening here. 2, 4, 8, 16, 32, etc., etc. And the first thing we want to do to this is show it compressed horizontally. So we're going to do K first. We're going to compress it horizontally. So every point is going to be cut in half with respect to the y-axis. So we're going to go through, instead of going through 1, 2, you're going to go through 1, 1. Instead of 2, 4, you're going to go through 2, 2. Instead of 3, 8, you're going to go through 3, 4. Okay? So now on your next graph, and you can do this all on one graph, but because you have 3, we're going to do it on 3. So on your next graph, you're going to bring that new one over. I'm going to bring over our blue one. Okay? It's going through 0, 1. It's going through, instead of 1, 2, it's going through 1, sorry. I did something slightly, I said something funny. I didn't necessarily do something funny.
1, 1.
Yeah, I said 1, 1. But that's not correct. 1, 1 is,
Because you're doing half as much, so it's 0.5 and 1.
it's going to go through 1, 4.
Excuse me?
On the first one?
So it doubles?
This point, I drew this point. This point doesn't exist. Okay? This is 1, 4. This is 2, 8. No, it's 1.5, 8. Okay, I did do it right. I'm supposed to be splitting this coordinate in half.
Yeah, so it's 0.
So this should have been, I should have, yeah, 1/2. 1/2, 2 is that first point. And this one is 1.58. Okay, so 3 divided by 2 is 1.5. 2 divided by 2 is 1. 1 divided by 2 is 1/2. Okay, so I drew that now. And I'm going to copy it down over here. Same graph. And now we're going to perform our vertical stretch compression reflection, which is a reflection in the x-axis. So I'm going to take all of these, and the x coordinates are going to stay the same. The y coordinates are going to change to negative. So I'm going through 0, -1, going through 1/2, -2, going through 1, -4, and going through 1.5, -8. Okay, so it's just a reflection over the x-axis here. So all of these points should be equidistant from the x-axis. And now we're decreasing instead of increasing. And you can add the equation of what we've done so far as you move along. So in our first picture, all we did was 2 to the power of 2x. So this blue graph is y equals 2 to the power of 2x. That was our horizontal compression by a factor of 1/2. So that's right here as well, y equals 2 to the power of 2x. Our pink graph includes just our negative sign. So y equals -2 to the power of 2x. And you have a third graph, so we'll move over to our third picture. And we're going to redraw our pink guy, which is y equals negative 2 to the power of 2x. If it's helpful, you can rewrite some of the key points that it goes through. 0, negative 1, 1 half negative 2, 1 negative 4, and 1 and a half negative 8. And then we can draw our last graph. We're going to perform both translations. So we're going to, for the vertical translation, again, it's easiest to move the asymptote. Right now we have an asymptote at y equals 0. I'm just going to move that up 5. 1, 2, 3, 4, 5. So there's our horizontal asymptote, sorry. And so our vertical then, we're moving up 5. So instead of going through 0, negative 1, it's going to go through 0, positive 4. But we also need to move this thing to the right 3 units. So instead of going through 0, 4, it's actually going to go through 3, 4. Okay? So this whole thing moves up, and then it moves over to the right. And we try to keep the same curve. And if you want to, you can change all your coordinates. You can say, okay, because it's moving up and over, my new point here, instead of 0 and negative 1, it's going to go over 3 from 0 to 3 and up 5 from negative 1 to 4. Same thing here. It's going to go over 3, so from 1 to 4. And it's going to go up 5, so from negative 4 to 1. So the point 4, 1 is on the curve. Yeah, is that making sense?
Wait, is it?
So we're changing the x and y coordinate at the same time. This 1.5, if it moves over 3, the x coordinate is going to be 4.5. And the y coordinate is negative 8, but it's going to go up 5 to negative 3, which is somewhere over here. Okay? And then I can draw my new curve, which comes like this, and then curves down pretty steeply. And that new graph is y equals negative 2 to the power of 2 x minus 3 plus 5.
What?
Nice.
Okay, I'm also going to do an extended table of values and see where we end up. And I erased my work, but that's okay. So we've got x, y, and it's a exponential function, and the base is, we're starting with f of x equals 2 to the power of x. Okay, so when I'm doing this, I want to take some y's, some x's and y's that will be helpful. I'm going to take negative values and positive values. Okay, so we're looking at negative 2, negative 1, 0, 1, 2, 3. That's going to give us a pretty good idea. And then I'll just quickly put in the y coordinates that go with this. So 2 to the power of negative 2 is 1 over 2 to the power of 2, which is 1 over 4. And then I'm going to be doubling it each time. So 1 half, 1, 2, 4, 8. Okay, that's our starting point. It's an extended table of values. So I'm looking at stretch compression, reflection, translation in the vertical, and then the horizontal, same thing, stretch compression, reflection, translation. And my reference here from the problem is y equals negative 2 to the power of 2 times x minus 3 plus 5. We've already described all those, so I'm just going to work through it fairly quickly. Looking at our vertical, I have a reflection over the x-axis. So all of my y-coordinates just become negative. That would be here, reflection. And there is no stretch because the absolute value is 1, negative 1. So I can skip the stretch compression in the vertical and go straight to negative 1/4, negative 1/2, negative 1, negative 2, negative 4, negative 8. And translation vertically is going to be up 5. Okay, so this is negative 1/4 or negative 0.25. It's going to be positive 4.75. It's going to be positive 4.5. It's going to be positive 4, positive 3, positive 1, negative 3. I realize I'm not giving you time to think about that. I'm just getting it down. And now we can talk about what's happening to the x's. They have a horizontal compression by a factor of 1/2. So they're going to get cut in half. So instead of negative 2, we have negative 1. Instead of negative 1, we have negative 0.5. 0 is not going to change. Instead of 1, we have 0.5. Then we have 2 turns into 1, and 3 turns into 1.5. We're doing pretty good so far.
How come you do some decimals and some fractions?
Yeah, that's a good question. Do whatever makes you happy.
Mm-hmm.
Mostly because this one I wasn't multiplying by anything except the negative sign. And this one, when I was multiplying it or moving it, it was easier to think in terms of decimals rather than adding and subtracting fractions. But if you can add and subtract fractions on the top of your head and then convert them to where they should be on your coordinate plane, then kudos to you. Go for it. If you want to convert to decimals right away, you can do that too. It's just easier to think about this in terms of fractions. Okay, is there a reflection? No.
No.
So we're just moving these 3 to the right. So I'm adding 3 to every point that I see. So that's 2. This is 2.5. This is 3. This is 3.5. This is 4. And this is 4.5. And now I have all of my new coordinates that I could use to graph. I have 2, 4.75. I have 2.5, 4.5. I have 3, 4. I have 3.5, 3. I have 4, 1. And 4.5, negative 3. That'll give you a pretty good drawing. That'll come across like this and go down. Just like we drew. Not like that so much, but. Okay, extended table of values. Parent function, transformed function, x and y coordinates for the parent function, x and y coordinates for the transformed function. Okay, example 4, somewhat real-world situation. We have a circuit, and the current is measured in amperes, A, after t seconds, and it can be found using the formula. Example, I don't know what it's called in yours, example 2 or example 4? Example 2. And the formula given is I, with respect to t, is 0.9 times 1 minus 10 to the power of negative 0.044t. Can someone check that I copied that right?
You did.
Yeah.
Thanks very much. We need to graph the function using graphing technology, then determine the appropriate domain for the function, and what is the current after 2 seconds, what is the current after 5 seconds. So we're not going to graph it. It is a exponential function, but with all of this stuff happening to it, it ends up looking like this. And the x-axis, the horizontal axis, is t, measured in seconds. And the vertical axis is I, which is the current measured in amps. Okay? Amperes. But we want to talk about the domain. What is domain?
The input.
The input, the values that can go in. Well, we're talking about time.
Set of random
X,
So-
t belongs to set of random.
Such that t, is there any
Not
sense?
equals 0.
And
No, you
Negative.
can't go back.
Not go back.
It cannot be less than.
greater than or equal to talk about what it is.
I mean, you can't name
If you're talking about restrictions, like from the denominator, then it's helpful to say what t can't be. In this case, we're just talking about what t is. So I'm actually going to erase this whole back part because it doesn't exist. Starting here. And what else do we need to talk about? What is the current in the circuit after 2 seconds? So if you're on technology, you just, you scroll until you get x equals 2. And then you find out what the value of I is at that point. And
don't add 2 to your equation.
yeah, or you could do that, but that would be you're on graphing technology already.
Oh,
So yeah, if you didn't have graphic technology, you could put 2 in there and you could figure this out. And if you did it carefully in your calculator, you probably would get the right answer. But at
no problem.
2 seconds, we are at 0.17 amps. At 5 seconds, again, you'd be looking at your Desmos. 2, 4, 6, here's 5. You'd be going up and saying, okay, what's the value at that point? It's right here. And it ends up being 0.36 amps. Last thing, describe what is happening to the current over the chosen interval. So describe this blue curve where t is greater than 0. Describe what you see. What's happening?
There's a constant increase as the current.
As time
goes on, there's an increase
of your amp.
Yeah, so
Well, I said.
where t is greater than or equal to 0, function is increasing. What about the rate of increase? Is it increasing faster and faster, or is it increasing slower and slower?
Faster and.
At a steady rate.
Steady rate would be a straight line.
Yeah, guys,
Kidding.
come on. It's
Slower.
Yeah, the rate of increase is actually decreasing.
because it's a curve.
No.
Okay, so
it's
it is
curving down.
it is increasing, but it's doing it more and more slowly as time goes on. Is it ever going to curl and go back down?
No?
No, it's not.
That's not
Point of no return.
Listen, it's going like this.